Hello and welcome to NPTEL online certification course on aero engine gas turbine cycles. So, today we are starting with our third week and this week is dedicated to turbojet engines. So, we were discussing about the performance of different gas turbine engine components. We have taken the control volume approach for our inlet, compressor, combustion chamber and turbine as well as for the exhaust nozzle. We have gone through the discussion about the adiabatic efficiency, polytropic efficiency of both compressor as well as turbines. We were discussing about the shaft energy balance. We were discussing about what all are the need of these components. Now, let us see how do we use this what all we have learned for past 2 weeks for our engines. So, if we recall, this is very important for moving towards the third week. So, let me discuss it again. We have discussed about the ideal behavior and actual behavior of different components. Very first we have started with our inlet. So, adiabatic and reversible process we have considered. For actual condition it is adiabatic and non-reversible. We have introduced a parameter called diffuser efficiency. We have introduced one more parameter, that is pressure recovery factor. Second component what we have discussed is compressor. For ideal condition we have assumed that to be adiabatic process and reversible, and we have introduced two more parameters like pressure ratio and temperature ratio for the compressor. In actual condition, since this process is not a reversible process because of addition of the losses, the compressor work definition that is changed here. Here in this case we have introduced two different efficiencies, polytropic efficiency and our isentropic efficiency or the adiabatic efficiency of the compressor. Then we were discussing about the combustion chamber, where we have considered there is no total pressure loss and we were considering combustion to be 100% efficient. But in actual we have realized there will be losses because of screen friction in the combustor. At the same time we will be having losses in the combustion process, and that is the reason we have introduced a parameter called burner efficiency and the pressure loss. Then we were discussing about the turbine. Same way as we have discussed for the compressor, here in this case for the actual configuration we have introduced two parameters like adiabatic efficiency of the turbine and the polytropic efficiency of the turbine. And we have realized what all are the importance of this adiabatic efficiency and polytropic efficiency. Then very important we were discussing about the nozzle, and for nozzle also looking to the screen friction losses happening inside the nozzle, we have introduced the parameter called nozzle efficiency. Here in this case we were discussing about different conditions like nozzle to be choked and unchoked condition, and for that we tried to calculate the velocity that is coming out from our nozzle, and based on that what all we have discussed in week 1, that will be helpful to us in terms of calculation of thrust specific fuel consumption, thermal efficiency, propulsive efficiency, overall efficiency. So, here this is what we say. Now, the question is, when we are going for the gas turbine cycle analysis, as we have discussed in our first week, we are considering gas turbine engine as a black box at the initial stage. So, we are not having any information about the efficiency. So, in order to do the analysis more realistic way, you need to assume certain numbers, and these numbers if you look at for diffuser, it says the efficiency will be in the range of 70% to 90%. That is what is strongly depending on the flight Mach number, and we know this is because of the frictional losses which are happening inside the duct. When we consider say next component, it is a compressor efficiency. For that it says efficiency will be in the range of 85% to 90%, As of now, with the new engines, the companies, they are claiming this efficiency to be in the range of 92% also. Now, what all we have discussed is the losses because of friction, because of turbulence, because of separation, shocks, bleeding, cooling. These all things, that's what will be bringing the losses in the compressor, and that's the reason why we are having efficiency in this range. Next component what we have is burner or a combustion chamber, and we will say this is very efficient process, and that is the reason why efficiency will be in the range of 97% to 99%. We have one more additional component which we will be discussing in next week, that is what is afterburner, that is also having efficiency in this range. And what we realize, due to incomplete combustion, chemical composition, physical properties, thermal losses due to the conduction and the radiation, pressure losses because of screen friction and pressure drag, this all brings the efficiency term for combustion chamber. The next component what we have discussed, it is our turbine, and it says turbine, it is power generating device and which is working under favorable pressure gradient, and that is the reason if we look at my efficiency will be in the range of 90 to 95%. And here we can say the losses are because of friction, because of shock losses, because of mechanical losses. All these things, that is what will be bringing the efficiency term to be in a lower side. The important component as we have discussed is my nozzle efficiency, and it says we can assume safely in the range of 95% to 98%, and losses are because of friction, because of shocks. So, now you can say we are making our initial stage in order to assume these numbers. So, these numbers, it is very much acceptable throughout the industries, even for academia and for research purpose. Now, let us discuss about say turbojet engine. Here in this case, if we look at, we are having two engines, Frank-Whittle engine and one Heinz engine. So, before Second World War, these engines were under development and they were at the laboratory level for the testing purpose. After Second World War, say after 1945, people they have realized the importance of these jet engines, and they found this to be most suited for say transportation purpose, and they have realized the power to weight ratio, that is what is very high, the compactness and easiness in making these engines, and that is the reason why these jet engines are more popular. Here in this case, if you look at this one Ohain, he was in Germany, at the same time Frank-Whittle from England, they were working together, they are the originators, the beginners for the development of these jet engines. They were not knowing each other and their progress, their work. It says like in 1930, say Frank-Whittle, he has patent for gas turbine engine, this jet engine. At the same time, in 1936, Van Ohain, he has registered the patent. In 1939, Van Ohain's engine that was first tested for the flight condition, and later in 41 it was tested by Frank-Whittle. So, here in this case, if we look at carefully, this engine, it is comprising of centrifugal compressor, we are having combustion chamber, then we are having our turbine, those turbines were axial turbines, and we are having the nozzle. So, this is what is representing the cut section of the engine. Parallelly, it says the axial flow gas turbine, it was been designed by Professor Herbert Wenger in 1930. So, we can say this is what was the beginning for the turbojet engine era. So, almost we can say almost 90 years back. Now, in order to understand this, we say our turbojet engines, they are being classified as say with afterburner or without afterburner. They are also being classified based on number of spools, whether it is single spool engine, two spool engine, and for single spool the kind of compressor we are using. say axial flow compressor, centrifugal compressor, or the combination of axial centrifugal compressor. So, we will be discussing about this turbojet engine in detail for next 2 weeks, for week 3 as well as for week 4. Now, types of turbojet engine, if we look at, it says single spool turbojet engine configuration. Second configuration, it says with afterburner. Then we have 2 spool turbojet engine configuration and 2 spool turbojet engine configuration with the afterburner. We will be discussing in detail about the afterburner in later classes. Now, let us look at, say, this is what is representing our single spool turbojet engine. So, if you recall, this is what all we have used for our initial discussion about different components. This is J85 engine, where you look at, this is my entry condition, it says my inlet duct or the inlet diffuser, that will be followed by the compressor. We are having the diffuser, that is what is used to decelerate the flow before entering inside the combustion chamber. We are having, say, turbine, that is what is generating the power in order to rotate the compressor. Here, in order to connect the nozzle and turbine section, we are having jet pipe or the tailpipe, and last component, that is what is, say, my nozzle. So, there are different engines like J85, J47 by GE, Rolls-Royce Viper, VK1 for the MiG-15, Rolls-Royce Avon for Canberra B2. These all are the single spool engines. We can say they were the initial engines which were being developed. Now, there are special applications of these turbojet engines. So, small turbojet engines, they are having application for, say, cruise missile, for target drones, small unmanned air vehicles like UAVs and jetpacks. That is what is a major attraction these days. So, here if you look at, these engines are of small size which are having special application for the drones. Similarly, cruise missiles, we can understand our thrust to weight ratio for gas turbine engine, that is what is very high. So, many times for missile people, they are using, say, solid propellants, they are bulkier one. So, the range what we are looking for, it says we will be able to achieve higher range using these turbojet engines, and that is the reason why many cruise missiles which are existing, they are having, say, turbojet engines. Here if you look at, this is what is representing small turbojet engine which are used for UAV purpose. Here if you look at, this is what is very small, you can put it in your palm. This is for the UAV application, and here if you look at this jetpacks which is having, say, 4 engines which is been wired by this man, 2 on right side, 2 on left side. So, this is what is the future of our gas turbine engines. Now, here if you look at, there are different companies, number of companies, they are making small engines also. So, just realize when I say we are having engine manufacturing companies, the names that will come in mind is, say, GE, Rolls-Royce, Pratt and Whitney, Safran, 8 MTU engines. But parallelly there are small companies, they are making small engines also like Turbomeca, Williams International, Micro Turbo, Teledyne. We are having, say, our in-house development by HEL, by Mitsubishi. This all if we look at, they are having the thrust capacity in the range of 3 to 5 kilonewton, and they are having the compact size, and that is what is attracting the attention. So, now the thing is, people they are moving more towards, say, future war with unmanned kind of configuration, and it says like having this kind of engines that will make life easy, and that is the reason why lot of research and development activities which are going on even as on today for turbojet engines. So, here let us try to understand how do we put all these processes which are happening inside the engine. Say, we will be presenting our ideal cycle with inoperative or afterburner, the performance of this engine or the processes that can be represented on TS diagram. So, here we can say this is what is representing my atmospheric entry, from where the air will be entering inside my intake. Very first process we say it is my intake process, and that process we are assuming to be isentropic process. Then that air will be entering inside our compressor, where it will raise the pressure. So, the pressure will be raised from P02 to P03. At the same time, temperature also will be raised from say T02 to T03. The next component what we have is my combustion chamber, and we know it is nothing but the heat addition process, and this heat addition process we are assuming to be happen at constant pressure. So, we can say this is what is representing my constant pressure line. So, it will raise my temperature from T03 to T04. Let me highlight here this T04, that is what is a maximum turbine entry temperature, or this is a maximum temperature of this cycle. Now, from there this combustible gas that will be entering inside the turbine, here this expansion process we are representing by say T04 to T05, and this is representing the drop of pressure to P05. We need to be very careful here. The whole purpose for putting the turbine in aircraft engine, it is to run the compressor, and on TS diagram these pressure lines are diverging line towards say on right hand side, and that is the reason why you need to be very careful when you are putting or when you are plotting this diagram. Now, after pressure P05, it will get expanded inside the nozzle, and that process we are representing from say P05 to atmospheric pressure. So, this is what will be making a cycle. So, this cycle, that is what is named as Brayton cycle. People they used to say this as a Joule cycle. Many people they are defining that as constant pressure cycle. So, all this, that is what is same. So, we need to realize here our gas turbine engine, that is what is working with say Joule cycle or Brayton cycle or constant pressure cycle. Okay. Now, what we have learned, let us try to put that knowledge for explaining the actual cycle. So, here if we look at this is my atmospheric pressure, what we know from infinity to 2, that is what is happening inside my intake, where we are considering that process as isentropic process, and because of presence of losses we know our entropy, that is what will be increasing. So, my actual process that is represented by this red line. Now, from there my flow that will be entering inside the compressor, and this compression process we are assuming as isentropic process. We have realized because of losses present inside the compressor, my actual process will be different from my ideal process. Okay. Now, what we have assumed for my ideal cycle, my pressure in combustion chamber, that is what is remains constant, but we have realized in our last week that the process that will be reducing, or there will be loss of pressure in combustion chamber because of the screen friction, and that is what will lead to give you my point 4, that is what will be shifted towards say here, and it says there is a drop of pressure delta P0. Now, from there what we say is my expansion process. So, my actual expansion process, that is what is represented by the isentropic process, but for actual case we will be having that process that is represented by from 4 to 5. Now, what next component we are having, that is what is a jet pipe. So, we can consider this as a cylinder, and since it is a solid body, there will be drop of pressure, and drop of pressure that is represented from P05 to P06, and here where my temperature, that's what will remains constant. Now from 6 to 9, this is representing my expansion process which is happening inside the nozzle, and in actual condition we know my exit temperature from the nozzle, that's what will be higher than that of my ideal temperature. This is what is because of my actual cycle. So you can see, you can clearly differentiate my ideal cycle and actual cycle. Now the question may arise, why do we learn this ideal cycle as well as actual cycle? This is, we need to understand that actual cycle is a cycle based on which my engines are working currently, and that is the reason why this knowledge is very much important. So let us try to realize how do we calculate all these pressures and temperature, and what is the use of all calculation what we are doing, and how do we evaluate the performance of this engine. So let us see, here the process 0 to infinity to 2, that is what is representing my intake or inlet process. So my air that will be decelerated relative to my engine, and we can say my exit pressure and my entry pressure, that is what will be same. And here in this case it says my temperature, that is what is given in terms of isentropic correlation. What we realize, my actual process is different, and that is what is been differentiated by using the diffuser efficiency term. So this is my isentropic enthalpy drop by actual enthalpy drop. By using this correlation, we can get the outlet pressure from my diffuser is a function of my diffuser efficiency. At the same time, our outlet temperature, that is not the function of diffuser efficiency. So if you recall, when I was discussing the intake, that time we have discussed this process we are assuming to be adiabatic process, and that is the reason my outlet temperature of the diffuser, that is what is independent of the losses. So what is the use of this? Say it says we are able to calculate very important parameters like pressure and temperature at the exit of the intake, that is P02 and T02. Now let us consider the next component. What we say is our compressor, and this compression process, ideal process we are representing from 2 to 3, and we can write down our compression ratio is outlet pressure to the inlet pressure, and my temperature ratio we are correlating based on my isentropic correlation. Now in actual condition we have realized we are introducing the parameter called compressor efficiency, that is what is a function of my compression ratio and polytropic efficiency. Now based on that we can calculate what will be my outlet pressure, what will be my outlet temperature. Maybe compression ratio it's known to us, and based on that we can calculate our outlet pressure. Based on isentropic correlation we can calculate what will be my temperature at the outlet. So here very important parameter what we are calculating is my pressure and temperature at the exit of compressor, it is P03 and T03. Now next component what we have is my combustion chamber, that is what is represented by process 3 to 4, and we know my point 4 it is been decided based on turbine entry temperature. So there are metallurgical consideration, and that is what is putting the limit to my turbine entry temperature or turbine inlet temperature. Okay. So let us put combustion chamber, and if we will be doing our energy balance, we can say this is representing the amount of heat, that is what is entering inside the combustion chamber. Here this is what is my MF into lower calorific value of the fuel that we will be burning inside the combustion chamber, and as a product we will be getting M infinity plus MF into H04. Okay. Now If I will be writing my energy balance for the ideal condition, then I am able to calculate what will be my fuel air ratio. Okay. Now, in actual condition, what we know, because of friction we will be having the losses, and this losses that is calculated based on this correlation. It says my 2 to 5% losses, that is what will be happening inside the combustion chamber. And for the actual cycle analysis, we need to introduce the term, that is what is my burner efficiency. So, my correlation for the fuel air ratio, that is what will be changed here. So, be careful which relation, what analysis you are doing. Are you doing your ideal cycle analysis or actual cycle analysis? So, many times when we are doing our calculation, we about to forget this burner efficiency, and that is what will lead to give some wrong results. Let me put the point here. Suppose if I consider, I know what is my say turbine entry temperature, based on that I can calculate what is my fuel air ratio. There are other consideration where I will be knowing the number, that is what is fuel air ratio, and based on that I will be trying to put the turbine entry temperature. So, I am giving you the idea of reverse calculation, where people they are moving these days, say we are looking for specific fuel consumption to be as low as possible, because we are looking for the fuel economy. Okay. Now, when we say fuel economy, that means my burning of the fuel need to be lower, and that is what is been taken care by changing my temperature ratio. Okay. So, here we are able to calculate important parameter, that is what is my fuel air ratio. Now, let us move towards the next component, that is my turbine. For the turbine, as we have discussed, we need to balance the work between compressor and turbine. So, here we are introducing the parameter lambda, it is nothing but my mechanical efficiency. It says this mechanical efficiency will be in the range of 75% to 85%. Let me put the point here. These numbers now it has reached almost near 90% for say aero application. When you are talking to your friends, those who are in mechanical engineering, they will say mechanical efficiency can never will go to that number, but they are special devices. These aero engines are super special devices where we are able to achieve this kind of numbers, and that is the reason why it is a major attraction. Okay. Now, when we are putting our balance, I can write down say CPC T03 minus T02, that is what is equal to lambda, and here this is given by 1 plus F Cp T04 minus T05. Now, based on this correlation, we can calculate what will be my temperature, what will be my pressure. Okay. If we are moving towards the actual cycle, under that condition we are having the parameter, that is what is called my turbine efficiency, and if I will be using this turbine efficiency, my pressure correlation will be changing here, and if I will be putting this turbine efficiency and work balance, I will be having my pressure ratio or expansion ratio, that is what is a function of my compressor efficiency and turbine efficiency. So, we can calculate what will be our outlet pressure and outlet temperature based on this analysis. Now, here very important thing you need to observe, that is what is my gamma, that I have changed with the suffix H, that is what is representing my specific heat ratio that will be changing. So, when the combustion, that is what is happening, it says because of dissociation process we will be having the change in the property. The property is called Cp and Cv. Mainly if we look at Cp, that is what is a function of my temperature. Since my temperature is more than 1000 Kelvin, where this process, that is what will lead to change the value of Cp drastically, and because of that change of this value of Cp, my gamma value will be changing with. Okay. Now, let us move towards the next component. What we say is my tailpipe, it is process 5 to 6. So, here in this case what we have assumed? We are not having any losses, that is what is happening inside my tailpipe, and that is the reason why my P05 and P06 they are same. But when we are talking about the actual cycle, we have realized there is a loss of pressure that is happening here, and my temperature, total temperature, that is what remains constant. Okay. So, here in this case it says my P06, that is what will be equal to P05 minus pressure drop in the tailpipe. This also will be in the range of 2 to 5%. Okay. Now, here we are able to calculate the properties at the exit of our tailpipe. Now, let us move towards the next component, that is nozzle. It is represented by the process 6 to 9. Here in this case, as we have discussed, very first thing we need to do is to calculate the critical pressure. So, when I am considering my ideal process, that is given by gamma plus 1 by 2 to the power gamma over gamma minus 1. When we are considering our actual process, be careful. Here we need to introduce the property or the parameter called nozzle efficiency. Okay. Now, once we are calculating our critical pressure, then we will try to compare that critical pressure with the atmospheric pressure. So, we have discussed earlier, when we are having our critical pressure that is greater than my atmospheric pressure, we can say the nozzle it is under choke condition. And here in this case, we need to consider exit pressure as critical pressure. Okay. When I say we are considering exit pressure as critical pressure, we are able to calculate my temperature ratio. Here this T06, that is what is known to us. From this correlation we can calculate what is our T9, that is my exit temperature from the nozzle. Once we know what is the exit temperature from the nozzle, we can calculate what will be the exhaust velocity. Same way, just try with. Here we can calculate this exit temperature and we are able to calculate what will be our exit velocity. Okay. So, maybe just try to write down the correlation where the nozzle is under unchoke condition. What you know? Let us see. So, when I consider my nozzle is unchoke condition, that means my critical pressure is lower than that of my atmospheric pressure. Under that condition, I need to consider my P9 equal to P infinity. And here if we are putting that correlation, we are able to calculate our temperature. We can calculate what will be our exit velocity based on this correlation. When we are talking about the actual case, we will be having the nozzle efficiency term, that is what will be coming into the picture. So, here we are able to calculate very important properties like pressure, temperature and velocity at the exit of the nozzle. Now, after doing all this, the next target for us is to calculate the thrust. So, just realize the equation of the thrust. It says m infinity into bracket 1 plus f V9 minus V infinity plus P9 minus P infinity into A9. So, here in this case you can understand why we are doing the whole cycle analysis, why we are calculating all the properties at the entry and exit of these components, because we want to calculate what is the exit temperature from the nozzle, what is exit velocity from the nozzle and what will be my exit pressure. Once we are calculating this thrust, we can calculate the thrust specific fuel consumption, that is m dot f divided by T. We can calculate our specific thrust, that is what is given by T over m dot A. We have our properties, we know our propulsive efficiency, that is what is given by thrust into flight velocity divided by thrust into flight velocity plus 1/2 m V9 minus V infinity square. We can calculate our thermal efficiency based on this correlation, where denominator will be MF into QR. This QR is nothing but it is lower calorific value of the fuel. Now, once we calculate our propulsive efficiency and thermal efficiency, we can calculate what will be our overall efficiency. So, now just realize why we have made our week 1 discussion in detail, why we have discussed the parameters in week 2 in detail, because all this that will make your initial foundation strong, and based on that we will try to analyze, we will try to understand these engines. Okay. So, in order to build the confidence, let us take this numerical. It says UAV company is planning to build single spool turbojet engine for their special application. The initial data considered for the design are compressor pressure ratio, turbine entry temperature, it is 1200 K, air mass flow rate 15 kg per second, isentropic efficiency for the diffuser is 1, it is 100%, compressor efficiency is 85%, combustion chamber efficiency is 98%, turbine efficiency is 89%, nozzle efficiency is 94%, and it says turbine shaft mechanical efficiency is 85%. The pressure loss which is happening in combustion chamber is 3% of delivery pressure. Pressure drop which is happening in tailpipe is 2% of delivery pressure. Here this is been designed for the flight condition, say sea level condition, that means my non-flight condition. So, my M infinity will be 0, my temperature is 298 Kelvin, pressure is 101.325 kilopascal. It says assume Cp of air as 1005 joule per kg Kelvin, take gamma equal to 1.4 for the air. For hot gas, my Cp value you can see here, it is 1156 joule per kg K, and my gamma is 1.3. The heating value or lower calorific value of the fuel is 43,100 kilojoule per kg. Now, it is your duty to suggest the nozzle area required, nozzle radius, exit velocity, net thrust, thrust specific fuel consumption and efficiency of this engine. So, based on all the data information that is what is given, very first step what you need to do is plot TS diagram. Based on available information, try to put them on plot that will build the confidence, and you will not make any mistake in terms of understanding. So, here we are stopping with this lecture. We will be solving this numerical in next lecture, and we will move forward with the other conditions for this turbojet engine. Thank you very much for your kind attention.